All right. Hello, class, and welcome to Part B of this lecture on Lambert's problem. In Part A, we defined the problem and went over some history. And in this Part B, we're actually going to look at the solution to Lambert's problem, Lambert's equation. And then in Part C, we'll cover a very simple numerical algorithm for solving it. And then we'll conclude with a numerical example. So to get started, let's review where we are. All right. So we have a target. We're focusing on the targeting problem. So we have a target, and we've determined its orbital elements, presumably through, again, an application of Lambert's problem, observing it at 2 points in time, perhaps. And we have a path, and so we want to find a target destination for our interceptor, or whatever this happens to be. So our goal is to determine this arc right here, from where we are at T1 to where we want to be at T2. So determining where we want to be at T2 is just the brief subject of this slide, where we have the orbital elements and we have the time at which we would like to intercept the target, delta t. And so since we have the orbital elements, this is just a rehash of Kepler's problem, where we're trying to propagate the orbit. And so we just do that. We calculate our true anomaly at this point. We determine our mean anomaly at that point. We use that with the mean motion of the orbit to get the mean anomaly at the target destination. And we use the mean anomaly through Kepler's equation to find the eccentric anomaly at T2, and hence the true anomaly at T2, and hence the position vector at T2. Okay. So what comes out of that is this. So we've calculated this arc of the trajectory to figure out where we want to be at the time where we want to be there. So that's pretty straightforward. Again, rehash of material from previous parts of this course. So the actual hard part is then determining the pathway through space by which we get there in the amount of time we are allotted. So we have an initial position, a final position, and we have a delta t, which we have, that's our amount of time we have, or time of flight, which we have to get there. So if we look at this problem, right, which is Lambert's problem, we can look at this problem. We know several things about this orbit, right, this intercept orbit. For example, we know two positions within this orbit. We know a position at one point on the orbit, and we know a position at another point on the orbit. Of course, given a position and velocity vector at any point on the orbit, we would be able to uniquely determine the orbit. But that's not what we have here. What we have is two position vectors on the orbit, and that is not enough to uniquely determine the orbit. Fortunately, however, we have a little bit more information. We have the delta t between these 2 points. And so we can use that to, in Lambert's problem, to solve for the transfer between those 2 points. Although, again, at some point we'll discuss the fact that this transfer is not necessarily unique. But that's for later on. We know a couple other things. So first of all, given R1 and T2, we can determine the orbital plane. We'll talk about that shortly. What we also know is the change in true anomaly between these 2 points. So remember, the true anomaly is the angle from the periapse to the focus, but we don't know where the periapse is, unfortunately, on this point, because we don't know where this distant focus, so we don't know where the line of the major axis is. We don't know this point, this line. So the change in true anomaly is again, still not enough to help us out. It's not gonna solve our problem for us. What we need to do is somehow figure out either A, what the distant focus is, where that distant focus is, the hidden focus as I call it, or what is the semi-major axis of the orbit. And it turns out the semi-major axis is what we'll solve for first, and then we'll use that information to determine the focus of the distant focus of the orbit. So this is a problem which is relatively uniquely defined. I say not really here because there are actually many cases there. I don't want to get into trouble, for saying something that's not true. I'll show it. Show why it's not uniquely defined all the time later on. But it's more or less uniquely defined given these 3 bits of information. And the piece that we really need to know is how this time of flight affects the semi-major axis. And that is Lambert's problem. Once you have the transfer orbit, you can, of course, simply calculate your delta v's by finding your initial velocity, v0, if you will, at t1, and calculate the velocity of your interception of the point in your orbit, right? Since once you have this orbit, you have its orbital elements. It's a little bit easier than that. So that's not actually the route we go, but right. So given the orbital elements, given the transfer orbit, we can of course determine the velocity at this point. Right. And then the difference between the velocity that we're heading at and the velocity that we need to be on that transfer orbit gives us our delta v vector, right, which is of course a vector. Unlike, of course, Hohmann transfers, there's no easy way of minimizing this number. I mean, you can do searches over, say, transfer times and so on and so forth, but it's a very difficult problem to try and minimize the delta v, and we're not even going to address that problem in this course because it's a hard problem and there's no easy answers to it, which I guess is repetitive. In any case, so the focus then is on determining what is that transfer orbit. So here I have almost a collage of illustrations of the Lambert's problem. I'll just highlight our transfers in each of them. Right. Now, as I said, we have these 2 points on this transfer orbit, R1 and R2. And so, again, that R1 and R2 allows us to uniquely define the orbital plane of the problem. Now, we're not going to actually solve for the orbital plane explicitly, but because those 2 points fix the orbital plane, right, the fact that we have 2 points in the orbital plane, and of course we have a focus, right? We know where the focus is. The focus is on the gravitational body, Earth or whatever. And so we have an orbital plane, which we know we have to stick with, right? There's no flexibility in that. There's no way of getting from R1 to R2 outside of this plane, right? Because you're moving in an ellipse. This is one of those basic limitations of navigation in space, right? You have to stick with your orbital plane, right? But what it does allow us to do is reduce the problem to something which looks a little bit more tractable, specifically something which looks two-dimensional, a little easier to deal with. So all of these illustrations are of two-dimensional transfers. Okay. So again, right, we also know that I mentioned the change in true anomaly from R1 to R2. But again, there's also ambiguity in that number, although we won't focus on it, in that we don't actually know if this is the change in the true anomaly or if this is the change in true anomaly. So either of those could be the case. So for example, we have this one that corresponds to what I call the retrograde solution, and the theta itself corresponds to the posigrade solution, if you will. So even given a transfer orbit, right, there's two ways of navigating from point A to point B on this orbit, right? We can take the long way, or I don't want to say the long way because that actually means something else, or we can take the short way, like that, which is now green, apparently. So again, right, already some ambiguity, and it turns out that this, for reasons which we'll discuss later, this change in true anomaly is not terribly helpful to us. So again, does not help us in uniquely determining the orbit. So for example, just to illustrate that ambiguity, so a fixed true anomaly, these arcs, you see lots of arcs on this diagram, these are all possible transfers from point R1 to R2 with the same arc between them, right, with the same theta between them. Right, so that theta is not going to help us overly much. So what is going to help us is the time it takes, because obviously not all of these arcs take the same amount of time to get from point 1 to point 2. Right? But it does limit us, right? you can sort of see this this issue of navigation in space again, right? We are limited to arcs that look like this. We have strong restrictions on the geometry of our transfers because space travel is not as simple as it seems. So what's the missing piece of information that we can use? Well, the missing piece of information is delta t. So delta t, in terms of time, right, doesn't really give us geometry. It's a temporal thing. The only way we can use delta t to determine geometry of the transfer is through Lambert's conjecture. And so Lambert's conjecture, the original formulation, was that the semimajor axis of the orbit only depends on a transfer orbit, right? In general, of course, the semimajor axis depends on period. But the semimajor axis of this transfer solution only depends on the delta t between these 2 points. Okay. So furthermore, we have Lambert's equation, right, which gives us an explicit relationship between those two between those two values, specific delta t and semimajor axis. Now, it's a little bit complicated. This is actually a much more modern formulation of Lambert's equation. Lambert did not formulate his equation. He did formulate an equation, but it wasn't in this format. This format is a little bit easier because there's less sign ambiguity, and it's a little bit easier to translate into numerical algorithms. But you see, right, A depends there, so it seems like there's a one-to-one relationship. But it's the dependence on A is actually hidden inside these parameters, which don't have a good geometrical meaning that I can figure out off the top of my head. So these are all functions of A. So in particular, given in A, we can calculate these parameters, alpha and beta, using these formula, which are given right here. So given A, we can calculate these parameters. And then we can get a delta t from that. But as you see, right, this complicated relationship between A and delta t is not easily invertible, right? And we'll come back to that in part C of the lecture when we talk about how to actually solve Lambert's problem. Because remember, what we have is we're given a delta t, and we would like to determine the geometric parameter A of this transfer orbit. But before I move on to explaining how this solution, the A, allows us to determine the transfer orbit, the geometry of the transfer orbit, I should explain these expressions a little bit more. In particular, two parameters which show up, S and C. So there's C and there's S. So these two parameters are parameters of the triangle which we see given here. So give that a color. This particular triangle, which is the triangle determined by the 3 points we have in this orbital plane. Specifically, we have the focus, the known focus, right, not the hidden one. We have R1, which is a vector, and we have R2, which is a vector. So these two things are A, the chord length. And so you may remember chords from, say, circles, right? As the points intersecting or connecting 2 points on the circle. The same is true of an ellipse. So the chord length is this length of the triangle there, see? And it's easy to calculate because it's just the vector, the magnitude of the difference between R1 and R2. So it's just the magnitude of the vector from R1 to R2. The next parameter is the semi-perimeter, which is half of the perimeter, right? Don't confuse it with parameter, which is a word we've used quite often in this course, but perimeter, the perimeter being of the triangle. So we have one length of the triangle, and then of course we have the other two lengths of the triangle because those are just R1 and R2. So the perimeter of the triangle is R1 plus R2 plus C. And then, of course, the semi-perimeter is half of that. Right. So those are two geometric parameters we have just given the geometry of R1 and R2. So those are based solely on R1 and R2. So you can calculate them based on those two position vectors. They come in here. They don't change with delta t, and they don't change with a. They're fixed. Don't change with a. Right. So here we have an expression which, given an a, will allow us to find a delta t. But of course, we actually have the delta t and we want to find the a, right? We're given delta t and we want to find a. But let's assume we've solved that problem. It's actually the subject of part C of this lecture. But let's assume that you found a numerical algorithm or some method, and there are several of them, Gauss gave one, for inverting this equation. So given a delta t, find a, which satisfies this equation. Turns out that solution is actually not unique, but we'll again address that problem later. So again, right, the proof of Lambert's equation and Lambert's conjecture were actually only proved in much later with, who was it, Legendre, I believe, in 1776, which is actually the year before Lambert died, in 1777 of tuberculosis. So I'm not sure if he ever actually knew that his problem had been rigorously proven. He probably wouldn't have appreciated it anyway, since he figured he already proved it. So yeah, Lambert, brief mention of Lambert. He was originally a clerk for his, I believe it was his father, not a very nice guy, I believe, in iron mines, and then was a tutor, very working class background. But again, he moved up in life. So I'm not going to give a history of Lambert because I just basically not many good stories to tell. In any case, so here what I've done is I've plotted, I haven't done this. I pulled this from a book, of course. I've plotted that equation, the Lambert equation, as a function of a. So given a, right, we have various values of t. So what you may notice is that for a given a, there's actually two t's which correspond to that solution, and that's given by that sign ambiguity we saw over there. Here's a sign ambiguity. Right? So that's a problem, right? In that basically what we're given is the delta t, and we want to determine the a based on that. So how are we going to be able to find that? Well, the solution, again, right, for a single arc is unique. This is actually there's two solutions to, what we've drawn here is two parts of the solution, the long way and the short way. And there's actually another set of solutions for a single revolution orbit, which is retrograde orbits for both of these arcs. And then we actually have multi-revolution orbits, which complicates this problem immensely. But in any case, if we limit ourselves to a particular arc of this plot, then we should be able to, given a t, find ourselves an a. And we'll show how to do that using bisection in the next part of this lecture. So just assume at this point that we can, given a delta t, we can find that a. From this plot, you can see, at least on this set of this arc, the solution is unique. Again, illustration. Okay, so assume we found our geometric parameter a. How does this help us determine the rest of the orbit? Right. So assume we're given a now at this point. So we've used our delta t to find a. And now we want to use our a to determine the rest of the orbit. So what we really need to find out is, where is that distant focus? Right. So where is that focus? So is it over here? Is it over here? Somewhere like that. So for this, to solve this problem, actually, it's actually not that complicated. We just use a very simple property of elliptic orbits, or ellipses in general. Specifically, remember we assume that R1, here this is R1, and R2 are on the ellipse, right? Because, right, that's our transfer ellipse. They have to be on the ellipse. So R1 and R2 are on the ellipse. The focus is here, and we want to determine this point, F prime, hidden focus. So how do we do that? Well, we use this very basic property of an ellipse. So the property of the ellipse that we use is the fact that on an ellipse, for any point on the ellipse, the sum of the distances to the focus, to the foci, so R1 and R2, right, that the sum of R1 plus R2 equals 2a for any point on the ellipse. So, okay, that's interesting, but how does it help us? Well, how it helps us is because now we've got the geometry here. We have R1, the focus here, right? But we don't know where this point is. So let's unpin this point because it's indeterminate. And then this is geometry, right? This length is R2, let's call it. And so this length here, we know its length, it's 2a minus r. And so if we are searching for the possible locations of this hidden focus, we know that it must be exactly distance 2a minus r from this point R2. And so we can just sweep out a circle about that point of radius 2a minus r. And we know that the hidden focus must lie somewhere on that circle. That's focal circle 1. Well, actually, technically, it's focal circle 2. And that's actually a 2. Yeah. Can't get all my typos out. Right. Likewise, so that information is still not enough to determine where our focus is. So we have an infinite number of points. We've got the entire circle of possible distant focal locations, or hidden focus locations. Fortunately, however, we have another focal circle, specifically about r1, right? So specifically, we know that the distance, this distance from r1 to the focus, the same focus, right, satisfies the same geometry, and so that distance must also, right, be 2a minus, in this case, r1, not r2. So r1 and, of course, r2 are different, so the circles will have different radii. So now we can sweep out a new circle. Let's just change that color there a little bit. About r1. Of radius 2a minus r1, right? We know a, we know r1, and here we know a, we know r2. And so the possible hidden focal locations for the second focal circle lie on this, well, in this case I've drawn it, it's a bit larger. Again, an infinite number of possible locations for the hidden focus. However, if we note that the focal location must lie on both circles, right? Then we have, fortunately, restricted ourselves to only 2 points, the intersection of these two circles. So we know that the hidden focus, given a particular value of a, must lie at either this point or this point. This gives us only 2 possible focal locations. And actually, both of those are a valid transfer orbit for a given value of a. Right. So, right, we can use delta t to determine a. We look at a, and now we note that there are 2 focal locations, which give us, which are valid for that particular value of a. So these 2 locations correspond to 2 different solutions. They're the long way and the short way. That's what we call them. There's actually, that's what they're generally called. There's actually for each of the long way and the short way, there's a retrograde and a posigrade direction to those transfers. But the orbit themselves, so the short and the long, refer to the orbits. So in particular, for this problem here, our focal points, I think this corresponds to the same geometry roughly as over here. Yep. So for focal point 1, possible focal point 1 we have here, and possible focal point 2 we have over here. So those correspond to different orbits. Right? So there's one, and there's the other. Right? So, like I said, right, the long way and the short way are differentiated somewhat by the fact that one looks longer than the other. Right? So, in particular, the short one is this one, the dark one, and the long one is this one. So for a given a, there are 2 possible orbits, right, that correspond to this solution. Of course, in addition, for that given a, for a given a, there's also, of course, 2 other solutions to this, which are the same orbits but different directions. So you could get from point A to point B going this way. Or you can get there going this way. Right? So I refer to this as sort of the retrograde path. And this one as the posigrade path. So this again for a given a. And then of course on the long way, or the long orbit, I should say. I should really say the long orbit. That might be a bit clearer. The long orbit. or the short orbit. Again, it's not clear because you can go the other direction as well. We can either go this way, right, or we can go this way. Right. So you've got to make sure, given your A, that you're on the right path, right? You're on the right orbit and the right arc, right? So whether you're going this way, and whether you're on the blue or the green. So actually, yeah, okay, good enough. Complicating the matter further, right? For a given A, again, you could actually, sort of double up and say, well, I'm going to transfer all the way around and back again, right? That's called a multi-revolution solution. And so again, when you're coding up these numerical algorithms, you want to make sure that you're looking over all of these possible solutions as you search through your possible A's. Right? So technically, there's actually an infinite number of solutions to this problem for a given A. Again, your delta t, however, is going to limit yourself to one of those arcs. However, you need to make sure you're looking over all of them because many of them may have actually a solution. So to illustrate that point, here I've got a very nice plot of these multi-revolution orbits here, given a particular value of A. So for given A, right? So let's look at this for given A first. So for given A, there's an infinite number of ways to get from point A to point B. The first is the long way or the short way, and then there's the multi-revolution versions of each of those. And here we've he only plotted out to, let's say it looks like 4, 5, 6 revolutions, n equals 6. So again, for a given A, there's an infinite number of possible paths. However, not many of those paths will actually achieve your desired delta t. Right? So, what you've got to do is remember the problem is reversed. We're given a delta t and we're searching for A. Right? And so that makes the problem a little bit complicated. So now let's reverse the problem and say we're given delta t, find your A. Right? So this problem is also complicated. So in particular, if you account for multi-revolution solutions, right, then there are multiple A's which achieve that delta t. So for example, here we've plotted for a delta t of 7.6 in canonical units. And we have 1, 2, 3, 4, 5, 6, 7 possible solutions. Right? So this in figuring out which solution is correct, right, is one of the banes of Lambert algorithms, and this is what makes them particularly temperamental. Right? If you limit yourself to a single revolution, the problem is a little bit simpler, right? So if you assume that there's only going to be one revolution on your orbit before you get from point A to point B. And again, these problems are more relevant for the orbit determination problem than for the transfer targeting problem, but that's okay. So if we're limiting ourselves to the first arc, right, of this orbit, this problem is still a little bit difficult because somehow you've got to determine if you're on this part of the arc or if you're on this part of the arc. And so I'll actually, in the next slide or two, I'll give a method for doing that. Right? So particularly, we'll compute this time, TP, and if your transfer time is above that, you're on this arc. And if your transfer time is lower than that, you're on this arc. So this is this corresponds to the minimum energy orbit. Right. So okay. Again, some of the problems with Lambert's problem. The solution we give to the algorithm we give in this course actually only applies to this arc, right? The bottommost arc, because we generally focus on the targeting problem. Also, by the way, of course, if you want to account for the long way, you have to do a correction where you take the period and so if you're going delta t, right, this the other direction is t, the period of the orbit, minus delta t, right? So you can also actually plot those as well if you like. So again, the problem is complicated. For short transfer times, the problem gets much simpler. You don't have to worry about these things as much, right? So okay, let's examine that question so sort of get started on that question I posed, which is, what is this point right here? Right. So this is the point where there's only a single arc, right? Or where there's only a single sort of solution to t for a given a, right? So that's what does that port correspond to? So if we think about, go back to the geometry of the transfers a little bit. Let's do that. Let's examine what happens to these transfers as we continuously vary this parameter a. So remember what our geometry is. Here we've got R1, R2. Here we've got R1, and we have a as we vary a, right? So say we increase a. So, right. As we increase a, right, remember the distance of the focal circles, right, from the points R1 and R2 are going to decrease, right? Because remember what those lengths are, right? This is 2a minus R2, and these circles are, right, 2a minus R1. Right, so as we increase a, the radius of these circles increases, and as we decrease a, the radius of these circles decreases. So let's examine, first of all, what happens when we decrease a. Well, as we decrease a, right, these circles get smaller and smaller. And remember what we're looking for. We're looking for the point of intersection of these circles. So this point, this point, this point. Let's see, get some more circles here. This point, this point, this point. Also, here, I'm having trouble visualizing. Right, here we go. This point, this point, this point. So as we, actually, I don't think you've drawn it quite right. But anyway, yes, these actually should, the focal points over there should follow that curve as well. Anyway, so as we vary this radius, right, as we decrease it in particular, these circles get smaller and smaller until at some point they get so small that they no longer intersect, right? At which there's no intersection, or there's only one intersection, this point right here. So this point right here, it corresponds to a min. And if you decrease a any further than a min, there's no solution at all. Right? So let's examine that point, right? What is this a min of which we're talking about? So if we just draw this little triangle here, right? Make sure we're So if we, yeah, so I'm probably not intersecting the right circles. So this is circle 1, this is circle 1, circle 1, circle 2, circle 2. Yeah, okay. Yeah. So those are not the intersections of the right circles. Yes, so what was I saying? Oh, yes, right. So, right. So at this point, right, this is the intersection of the circles. This is R1. I should use a smaller pen. This is R2. This is R1. And at this intersection, right, it lies on both circles. So this distance, right, along this length must be 2a minus R1. In this R2. In this distance here, again, lies on the circle about R1, so it must be distance 2a minus R1. Right. So circle 1, circle 2, right? Right. So this is 2a minus R1, and this is 2a minus R2. So the chord between those 2 points on that triangle that we talked about earlier, this chord must be the sum of those 2 numbers, 2a minus R2 plus 2a minus R1. Right. So for that minimum a, right, the chord length is equal to 2a minus 4a minus R2 minus R1. And of course, the geometry of the problem is fixed. We know where R1 and R2 are. And so we can actually calculate this chord length, right? It's that norm, R1 or R2 minus R1. It doesn't matter what the sign is actually. And so actually we can figure out what the minimum A is here, right? It's just this chord plus R1 plus R2 divided by 4. Right? So the minimum A, for beyond which, or below which there is no solution at all, is given right here. And that corresponds on this plot, right, to here, A min, beyond which there's no solution at all. Then, of course, what happens as we increase A, right? Well, then there's anything beyond A min, right? We'll have 2 intersections. And as we get, at A min, of course, right, there's only 1 point of intersection, right? At A min, therefore, we can conclude that the 2 options, the long way and the short way, coincide. Right? F prime and F prime prime coincide, so the long way and the short way are the same way. Right? Of course, but any A above those the 2 solutions for the focal point bifurcate. Right? So they split off, and as you increase A, it starts sweeping out a hyperbola. I don't have a proof that it's a hyperbola, but that it is, apparently. And furthermore, they get farther and farther away from each other, so they tend to diverge in opposite directions. So again, something about the geometry of the problem. Oh yeah, there's that A min here, right there, or chord length. And of course, corresponding to this A min, remember there's a 1-to-1 relationship between the energy of an orbit and its semi-major axis, because this is E equals negative mu over 2a, right? And there's a negative sign there. The A min also corresponds to the minimum energy transfer between these 2 points. Now that doesn't mean anything really. It just means that the orbit itself has minimum energy. That doesn't mean that it's a minimum delta V transfer, because remember there's this big difference, what we talked about in lecture 8 and 9. there's a big difference between the energy of a transfer orbit and or the energy between the target and the initial orbit and the delta V required to maneuver, right? So the minimum energy orbit, I say it's minimum energy, but I don't really have a good I mean, it obviously is the minimum energy orbit, but that doesn't really matter much, right? So again, hidden focus for the minimum energy orbit, F prime equals F prime prime for a min. That's supposed to be my at sign. Again, right, don't confuse the minimum energy transfer with the minimum delta V transfer for a two-burn maneuver, which is the Hohmann transfer. So again, not anything to do with the Hohmann transfer at all. And really, using the word minimum energy transfer is a bit weird. Right, so yeah, just things I said earlier. Right. So again, now that we've examined the problem, let's go back and solve it. And so we're getting set up here for the next lecture. But before we get started with that, we'll just go back to illustrate the problem we're solving, which is Lambert's equation. So that's Lambert's equation. And the problem is, of course, given delta t, find A. Now this is actually quite a hard problem, which is belied by its very simple structure. And in particular, if you're sort of like thinking that way, you can look at it, and it has actually a very similar structure to what you get if you use Kepler's equation, right? So this is, if you were to apply Kepler's equation twice for both mean anomalies, right, to find m1 minus m2, right, is n delta t, then divide by n, right? So each of these has a Kepler equations, equals E minus E sine E, right? So if you were just to subtract those two and then divide by n, you would get this equation, right? But this equation is, well, not particularly solvable because, right, you don't have E, right? But structurally, it looks actually quite similar to what we get with Lambert's equation, but don't confuse the two. So not usable. So big X that out. So again, while Kepler's equation was relatively easy to solve, Lambert's equation is much harder. For the reasons we gave before, in particular, it's not very well behaved. It has two arcs, right, where it's behaving differently on both arcs. It's not monotonic. So if you remember what Kepler's equation looked like, and like something like that, this is monotonic. It means it's always going in the same direction, which is up. Here it's going up here and it's going down here, so it's bifurcating, so it's not a one-to-one solution. And so solving Lambert's equation is actually significantly harder than solving Kepler's equation. And hence why we're going to devote another part of this lecture specifically to the problem of solving Lambert's equation. But I'm going to take a pause and come back to that question in part C.